Okay, good afternoon. So we'll move on from accelerated gradient descent to other important topics. So let's recap our discussion on how we motivated accelerated gradient descent. We talked about different classes of functions and their convergence, Lipschitz continuous, and strongly convex, Lipschitz smooth and strongly convex. And we discovered that there's some gap, and the gaps are basically, in the case of smooth functions and smooth and strongly convex functions, but mostly the smooth function regime, uh, right? And this gap is what you are trying to bridge, right? And this got us motivating. Well, is there something we can do with the fact that functions are well behaved, both from curvature upper bound and curvature lower bound perspective, right? And those are the two motivations. One was bridging the gap. The second is, can the next iterate have been influenced by a series of previous iterates? So the function is slightly well behaved, which means it's predictable, neither too curved nor too flat. Then you should be able to interpolate better, right? That's a key idea. So, and then we came across this variant we call the momentum version, where we have on one hand the gradient and the other is velocity accumulated. And then we also said this entire velocity can be applied, sorry, gradient can be applied um, right, at the original point, or you could apply the gradient at the new point. Um, so each of them gives a different variant. If you apply it at the original point, the option 1, you get something called heavy ball or Polyak. If you apply it after the momentum, then it's called the Nesterov momentum. So what can we do with respect to the Nesterov momentum? I mean, how fast can Nesterov momentum converge? Okay, so let's get a little bit more insight. Obviously, we're not going to discuss um, convergence properties. I'll give them as additional statements. The modified Nesterov momentum, which is after you get the current velocity, if you apply the gradient, you'll get convergence from 1 upon t to 1 upon t square. This is for Lipschitz continuous and strongly convex case. Okay. So, I mean, we wanted to get the log of 1 upon epsilon, you remember? So, this is not as good as that. So, just to kind of contrast this two again, right? So, Polyak says you'll compute the gradient before update. At xt, you compute the gradient. And Nesterov says you'll compute the gradient after the update. So let's understand each of them a little carefully. So Polyak's heavy ball momentum, what does it do? It lets you compute the current step gradient and then add momentum. This is a momentum. The one in red is momentum. Okay, so this is the important update. Xt plus 1 is xt minus alpha t gradient of f at xt minus mu t Now it turns out that its convergence has a slight difference. So in gradient descent was kappa minus 1 divided by kappa raised to t. Now you have a square root kappa minus 1 upon square root kappa whole raised to t. Well, you might wonder that, this, is there a difference? Does it make a difference if you replace? You remember what is kappa? Kappa is what? Strong convexity Lipschitz constant ratios, right? Or kappa is greater than 1 or less than 1? Sorry? It's greater than 1. So it's greater than 1. So what do you think? If kappa is greater than 1, which is better? Is there any kind of strong winner? If kappa is less than square root kappa is less than 1.5, as against if it's greater than 1.5, will it make a difference? Yes. Square root will be less. So there is some speed up. Convergences, but it's still not like a significant speed up, right? So you've got from you had L by 2. Slightly, okay? Slightly gone down. On the other hand, well, this is for smooth and strongly convex functions. Okay, that's important to note. Smooth and strongly convex. But if it's only smooth, it doesn't help at all. Okay. So it's comparable, commensurate with lower bound, and there's not much you can do. So by the way, this also matches lower bound. That's important. Right. You should have guessed that this is less just because it's a lower bound. You remember this was matching with a lower bound. So it's not doesn't much. I don't think you can do more, right? So yeah, strongly convex plus smooth case, we have both an upper bound and lower bound of the curvature already. So there's not much you can do. Plus in the smooth case, right? So smooth case you can't do much. Smooth plus convex, strongly convex, we exploited it. Smooth case alone, there's not much you can do. There's with an upper bound on the curvature. Okay. So the intuition is also written here. With just this alpha term, you're not exploiting curvature, but with mu t, you're exploiting curvature, right? Velocity empirically exploits curvature. So you should have some rationale on why we are managing to meet the lower bound. That's a rationale. Okay. So just to kind of again understand the difference between gradient descent and momentum, gradient descent was oscillating a lot by exploiting this curvature. You have specifically heavy ball, Polyak's heavy ball has reduced oscillation levels. Gradients are computed after computing the momentum. That is intuitive. Now nested out, okay, how does that perform? So remember there was a gap factor of T for the Lipschitz smooth case. Now can we exploit this or reduce this gap with nested out? Right, this in theory this gap is fixed. So can we do something? Post velocity update gradient computation. This is our target. This is what we want to do, right? The one in red. So it turns out Nesterow's accelerated gradient fixes this for smooth. So this is fixed for smooth and strongly convex, but Nesterov fixes this for the smooth case. Okay, this does Polyak does not fix the gap for smooth case. Now does Nesterov fix? So there's an unintuitive algorithm and a proof procedure. We'll not prove it in class. Okay, how it does it? There's some additional notes I've given. Generalized proximal projected gradient descent and a lot of convex geometry examples. I mean, geometry insights. In fact, the proof I give there is not just for accelerated gradient descent. It is for something called generalized accelerated gradient descent. Because it's even more general than this. So you'll find it very complex, the proof given there. So, but the tricks are kind of similar, right? Same bag of tricks you pull out some or the other. What is the algorithm? Okay, so algorithm intuitively you have a velocity based on the previous iterate. You do an update. And then after the update, you're going to compute the gradient at the new point. Okay, so we'll take yt plus 1 is xt minus gamma t. And then xt plus 1 is 1 minus mu t yt plus 1 plus mu t yt. Now there's a momentum here. So where is the gradient computation happening here? Can you explain the intuition? This is like the summary. So the point is gradient computation is happening before. So whether you do at the end or whether you do at the beginning is the same, right? We just simplified it by saying the first thing you do is gradient computation. So think of the gradient xt as the gradient after momentum in the previous iterate. So xt has got the momentum already. You understand? This is a simple. What I want to show on the slides is going to look a little bit more intimidating. So therefore, I drew the simpler picture first, and fortunately that will fit into the board as well. So I've been a little cognizant of board space. It's a different color. So what you do here is you compute this yt plus 1, which is the update momentum thing, right? Okay, so yt plus 1 is xt minus gamma t. So this is gradient of f of xt is the gradient from the momentum after the previous iterate. And then what you do is prepare for the next gradient update. Compute the momentum, right? So now you have yt plus 1 and now you're going to compute the momentum. xt plus 1 is a momentum update. Okay, so this is the you understand the step? It's the same as saying I'll do the momentum at the current step and then leave park the momentum from the current step for gradient computation in the next step. Instead of computing gradient in the current step, I'm just computing the same gradient in the next step. That's it. Therefore, I'm decoupling the yt from xt. Okay. So there's a kind of look ahead here, and therefore, even without strong convexity, even with smooth functions, you're able to get to a better convergence. Okay. So this gets you. This is first. Oh. With smooth functions, it gets you to from square by. So it has got you from L square by 2t LR square. It has reduced it to 3L by 32. Okay, so there's a lot of dirty math out there. Okay, okay, this is a summary. The takeaway of these two. So if you have kind of got this, now the details. Okay, this is the detail which I'm not going to write on board. The lambdas, how they contribute to the mu's, you'll see that. Okay, so now in the board you'll see lambda, gamma, etc. And the step sizes are important here. So you start with lambda naught 0, and you need to ensure that gamma t is greater than or equal to 0. So x1 is y1 is an arbitrary point. This is the same logic. Okay, so x1 is y1, and then there's no prior momentum, and then yt plus 1 is xt minus. So this is exactly the step I wrote here. Yt plus 1 is xt minus gamma t, gradient of f of xt. The same gamma, the gamma that is updated there, but each gamma is updated in terms of the lambdas, and the lambdas are obtained from the previous lambdas. Okay, this is a gradient descent on velocity. So the green part is based on velocity. Okay, yellow part is based on gradient descent. Right. So the green is xt plus 1 velocity update. Slide a bit further away than yt plus 1 towards the previous point yt. Now this mu t. So I had hidden there this lambda, but this lambda is lying buried within gamma. The mu can be just a function of t. Mu doesn't have any dependence on lambda or gamma. Okay, so the now why are these there? So I'm going to give you some additional slides, now it's the right time to give you some additional optional reading on this entire Goldstein conditions, RMO conditions, etc. Why these lambdas, gammas turn out to be. You need sufficient decrease, right? But you need to also look at how much the graph is tilted and so on. Basically, it's called a sufficient decrease condition. That's how lambdas and gammas turn out to be what they are. Okay, so are we set? You got an idea of what these two are. Okay. So this result comes by virtue of Nesterov. Therefore, the algorithm is called Nesterov. There's a theorem: if f is convex and Lipschitz smooth, then f of yt minus, so f is in, sorry, converges in terms of yt and not xt, right? Because xt is just momentum. What we want is gradient update. That is yt. So yt, f of yt minus f of x star is less than or equal to 2. This is the expression. Sorry. What have I said? Okay. Sorry, I made a mistake. This was our target. This is our target. We don't get there, but we get in a similar form. Our target was this. We are 3L by 32. What we get is 2LR square divided by T square, which is of the same nature. R square by L square. T square, sorry. Just make this correction, please. But it is of similar order, right? I don't think we will lose our sleep on this 32, so 3L by 32 L square by R square by T plus 1 square. We are fine with 2L R square by T square. Okay. Any questions on this? Okay, so we don't need F to be further strongly convex. And you're doing pretty well. So instead of T plus 1 square, we have T square. That's it. The denominator. Okay, by the way, I think I should show this. So this is Collab notebook where I also have carefully crafted many of these RMO conditions. So in fact, you don't even have to necessarily go through the slides I'll share. I'll just show you the Collab notebook, right? So I said this inspired by sufficient decrease condition, RMO conditions, Goldstein condition, and so on. So what happened? Yeah. So these Collab notebooks. So simple gradient descent with fixed step size. This is what we all do. But then I show what is Nesterov's accelerated gradient doing. Okay, so you can actually look at the number of epochs required for convergence. Some function value, you just make a note of it. Okay. So it's on the order of 2600. Now Nesterov's accelerated gradient descent, you run it. So the point is as follows: just because you have done Nesterov accelerated gradient and you have not given thought to the step size, you haven't really solved the world's problems, right? So then we are going to show, well, how gradient descent with RMO backtracking line search. Okay, so I've given the idea in what is as I said, right? They are largely corresponding to sufficient decrease. So find an alpha, or rather, no, start with an alpha, large value of alpha, keep dividing it by 2, so that there is a sufficient decrease in f of the w minus alpha g. G is a gradient, right? So each epoch is not just going to be based on some random value of alpha, but an alpha which for a given gradient helps you shrink best. So using that, oh sorry, this is function. I was trying to look. Oh yeah. So you see that the number of function evaluations was 250 to get to some value, right? And yeah, this is like the error. Um, now we have just got the same thing in fewer epochs. Okay. In the case of Nestor accelerated gradient, with the first condition you're not done very well, but there's a second condition which says I don't want to be just sufficiently small, but I want it to be sufficiently small with respect to some norm of g square. And then let's look at, okay, now just no, 34 function evaluations. You are pretty much there. Okay, this is interesting. While we got a factor half reduction using nested accelerated gradient, with RMO version 2, you're there much sooner, right? And then there's another line search where your alpha is itself obtained using some polynomial interpolation. Okay, your alpha is not random, but you look at how the function itself is changing for that given value of gradient. So it's like you see G transpose G is like a quadratic. And version 3, what does it do? Don't recall. Okay, so it wasn't really great. It's taking a lot of time. But then, okay, so now in 4, we basically take a min of. So there are issues. Basically, in each of them, I bring out issues. If you have a very large initialization alpha, you have a problem. So they do use some polynomial interpolation and have a fallback option. So with that, what happens is RMO version 4. Let me. Okay, so it took some 20 function evaluations. So backtracking is also important, by the way. I'm skipping over the backtracking and only looking at number of iterations. But if you're doing too much backtracking, well, for a given gradient, if I have to take 1,000 backtrackings, I'm in bad shape. But gradient computation is expensive, so I don't mind doing a little bit extra work for the alpha, right? So this is fine. Number of backtracking is 3, 20. This is very good, right? It's quite impressive. So then I also view the effect of the different line search techniques in a single plot here. Okay, here you can see. Fixed alpha is the blue one. It's pretty bad. RMO V1 we kind of messed up a bit. But in a life, you always start with the wrong step, and then we course corrected it to red. Or green was actually quite good. Then red. And the best of all was this purple guy, the last one, which had a fallback option on the alpha. Okay, so then, yeah, this is zooming into 50 iterations. 50 iterations, what happened? So RBO V1 kind of converged, and later on it again became slow, right? V1 was not bad, but it hit a little bit. It was hit a little bit later on. Okay, so the rest of it we look at, we see what happens if you use the V4 in many of the algorithms. So anyways, there are a couple of other step length choices. I also show conjugate gradient descent, but my goal was to show these 4. Have a look at them. It suffices to say that I talked about all of this largely to impress upon you the importance of step size. Okay. And some of these step size considerations come from this sufficient decrease condition. Is that okay? In case you were wondering, right? What is that magic going on here? Okay, so now kind of summing it up with all of these. So yeah, this is in my extra slides. I talk about the sufficient decrease condition. Basic idea here is I want to make sure that if this is a slight tilt to my gradient direction, beta t, right? So I need to make sure I'm at least I'm below this. I'm below this. I've decreased sufficiently. But there are other conditions which, like I talked about the fallback option, which ensure that I'm not overshooting either. Okay. So this is a basic idea. Line race search will consider some steps as alpha. We will next check if some sufficient decrease condition is met. If not, shrink the alpha. That's the basic idea behind all those algorithms. Okay. And the collab notebook link is provided here. Okay. So now, are we better than we were earlier? So we have accelerated SAGD. Okay. Now I've written in terms of number of iterations. This was in terms of accuracy. How good you are, right? When you put T, we are looking at how good you are in terms of accuracy. This is number of iterations. So in number of iterations, we are doing pretty well now. We have now square root epsilon, 1 upon square root epsilon instead of log of 1 upon epsilon. But still we are doing well for non-strongly convex functions here. Okay. So now, what are the other learnings from this collab notebook, right? So initialization of alpha matters. That's going to be very important. So take home that message that in some proofs I use some magic values of alpha, gamma, whatever step size. In practice, its choice is going to be sacrosanct. And in fact, even for theory, for some of the convergence proofs, it was important. So reinitializing alpha matters, right? You need to kind of reset the alpha once in a while. Otherwise, it'll become too small. So that's why I said the fallback, right? Get it back to 1. What else? What value one sets the alpha matters, especially when one is doing polynomial interpolation. So there was also a couple of those options, at least version 3 and 4, you would have seen G transpose G, some quadratic interpolation, right? What alpha to choose next. And yeah, accelerated gradient descent gets the direction using velocity as well as the step size. And it's slightly less sensitive. So that an important point is it's slightly less sensitive to the step size choice. I'm not saying it is not influenced or affected by, but it's like slightly less flaky. Okay, so you try and understand. Now I'll talk about the subgradient proof, a subgradient descent algorithm, which is in the spirit of the gradient descent algorithm. I won't be doing its proof, but the idea behind subgradient descent is, well, what if the function itself is not differentiable, right? The subgradients exist. How does it behave? And the second is, do all points matter equally for update? That's the next trajectory. So that leads us to stochastic. So there'll be 2 S, right? One is subgradient, the other is stochastic. So give some thought to these. In both cases, the proofs we will not be doing. Okay, proof of convergence. Okay, so now we have set the stage for the next set of next 2 algorithms. Both are S. Okay, so let's begin with subgradient. So a key concern here is there are lots of subgradients, right? The function is not differentiable. You've done that in your mid-sem. Which one will you pick? So here there's a challenge. You need to kind of keep track. You'll need to keep a, say, beam. So maybe it's a question, should it be a beam, right? The reason is I'll basically find a subgradient update. There's nothing much to discuss here. It picks some subgradient. But then you are no longer guaranteed descent. That's an important thing. If you recall, for smooth functions, we were able to even guarantee descent. Subgradient descent, I mean, I don't even know if the direction is a descent direction. Right? So what we do is we'll keep the best direction so far. Anyone has an idea why in the case of gradient descent you could think of descent? Any idea why? Hmm. No, but are you saying that if you have a gradient direction, there exists some step size for which the function will decrease? Is that what you're implying? Right, but you still didn't answer my question. Why? I'm making a subtle statement here, right? Which is I'm saying because because we are no longer guaranteed descent. So let me write this question down. In gradient descent, where we guaranteed descent. It's a question. Think about it, okay? When a subgradient, you're even embarrassed to call it a descent. Here's a subgradient algorithm. Okay, so I'll put this in bracket. You need to think about it. It's not difficult to argue. I just have to do a little bit of dot products and all that. Let's continue. So here what we'll do is you may have to keep track of multiple iterates, not one. So t equals 1 to t, capital T. So beam of subgradient updates, which means x1 is an update, x2 is, I put a superscript there. Yeah. Each of that is an update. And you're saying, well, I'll keep track of the functions, the points, and find the x which maximizes or sorry, minimizes function evaluation. So to update each t, there are basically two ways. You can either find a fixed step size or you have a diminishing step size. Now diminishing, okay, fixed step size, I'll tell you in subgradient descent becomes a little tricky because you're now you look understand that I have this function which is not necessarily differentiable, okay? And now based on some random, one of the random subgradient, the notion of subgradient was very loose, right? And I'm going to keep doing this. Maybe the sub-level sets are like this. I have no idea whether I'm drifting away, though I'm checking. I'm keeping track of the best so far. So there are considerations such as, also ensure that the gamma is diminished by design. Even with normal gradient descent, you do look at diminishing step sizes. But here, even in theory, to prove something, you'll need such assumptions. Okay. So that two assumptions. One is these gamma t's go to 0, but the series, right? If you sum of these gamma t's, then it doesn't diminish. Then it can go arbitrarily large. So this assumption is important. Why is the second assumption important? Intuitively. What is the problem if the sum also goes to 0? Sorry? Even if I keep moving in the same direction, you should be able to get the minimum. In one direction, you have a distinction, how much you can do. So every time you take a step, any other thoughts? Right. Oh, sorry. I'll give an example of this. So what is 1 upon square root t? What's the behavior? It will go to 0 as gamma t goes to infinity. But what's the summation going to be like? Will it go to 0? Or will it go to some finite number? Sorry. Obviously not 0. Finite number? No, right? 1 upon square root t? 1 upon t square? Huh? It goes to 0. So basically what we are saying, we are okay with 1 upon square root t, but not with 1 upon t square. Okay. So the main reason for this is that we are not very sure about the current step. So we want to be able to bail ourselves to bail out later on. Okay. So the intuition here is we want these step sizes to be small. But you want to ensure availability, ensure that you can escape false steps starts. Okay, so here small step size basically means gamma t goes to 0, but here you want to ensure that summation gamma t is in infinity, which means you can bail yourself out subsequently. Because you're not sure about the individual steps. That's very important. Okay, so it turns out that if f(h) Lipschitz continuous, which should be possible at least for a non-differentiable function. I mean, a function that's not differentiable everywhere. I mean, what I meant is it may not be differentiable everywhere. And if you ensure that there is some bounded initial condition, then f of x best is within of order of 1 upon square root t. Looks very bad, I understand. But this is kind of where we started. What was our first convergence? Sorry? Was it 1 upon t square? I don't think we began with t square. No, t square was like much better. We began with 1 upon t? Yes. I, in fact, began today's class, right? With a summary of all the. So it's 1 upon square root t is worse than what we have seen so far, which is making sense because it's after all subgradient descent. Okay. Now, if you have a fixed substep size, then you have something weird, right? F of x best is less than equal to f of x star plus some L square t. So that the t things keeps growing, right? As number of steps grows. So this is not very impressive. Well, this at least tells you it can converge. Okay, but then you have to take care of this gamma t's of that nature. Summation should be infinite, or summation should not have a lower bound, an upper bound. Okay, how do you prove this? I'm just highlighting important points here figuratively, so that even if you don't register the math, the key here is supporting hyperplane. That's how subgradient descent came up, right? Its existence is based on supporting hyperplane, so that's where you begin. By definition of the subgradient method, we just use a supporting result, hyperplane result. But we had assumed that we have some Lipschitz continuity, right? Can we use that? We can use that. So first we use this inequality and then do some completion of squares. Okay. So I again made this comment. What you do next is completion of squares. You have this term and then gamma ht square coming up. And then what you do, you kind of use Lipschitz continuity on ht square. So after you use Lipschitz continuity, you'll get L square. See, this is interesting. You'll basically end up getting gamma square, L square. And this is where the condition on gamma square comes up. So I didn't mention that, but yeah, we would like condition of gamma square, some condition of gamma square, right? We would like some condition on gamma, the summation of gamma square. Would you like at least summation of gamma square to go to 0? Like 1 upon square root t, summation square, so sorry, yeah, right? Summation of the squares will go to 0. Will have a upper bound. Will it go to the entities will eventually lead to a convergent series, right? Now, so constant gamma t is a disaster. So that is completely ruled out. So yeah, for diminishing step size, for constant step size, as I said, right, this is a little bit of a problem. You'll have gamma square L square gamma by 2. For diminishing step size, question is gamma t square less than infinity required? That's what I was hinting at. Is it required? We'll get this kind of expression here. So we must have gamma t square less than infinity. We did not add that, but now I'm adding it in retrospect. Gamma t's can go to the summation of the gamma t can have no upper bound. Okay, so with all of this term will go to will be something finite. This term actually we want it to go to infinity, right? So the denominator has gamma t summation. So now it's to our advantage. So summation gamma t denominator going to infinity, summation gamma t square in the numerator being upper bounded, overall results in this whole thing becoming 0 or tending to 0. Okay, so this is the reason why we were interested in the summation going to infinity. Okay, so yeah, basically with this kind of gamma t, r upon 1 upon square root t, you'll get this expression. You'll get ri upon square root t. That's how you get the proof, convergence proof. It's okay if you didn't get all the steps. Just wanted to highlight the intuitive process. Okay, so we have just added one more to our list. This is a list of honors, right? So, but somehow the subgradient method is far from honorable. We're not very happy with it. Okay, so let's register our story, convergence story here. So this has got us to, and we are writing everything in terms of, just be consistent, right? Everything is in terms of t. So we'll write the t part here. Okay. Now this brings us to, yeah, this brings us to the conclusion of the subgradient approach. The subgradient approach kind of requires a similar number of steps as Lipschitz continuous function. But so just to recall, the first Lipschitz continuous was very similar. It was 1 upon square root t. Looks like you didn't remember. Our first one was 1 upon square root t. So looks like it's not that bad. It's not as disastrous. So it's the same as gradient descent with Lipschitz. Lipschitz continuity. Only thing is we needed a lot more assumptions on gamma. Gradient descent convergence proof to 1 upon square root t was a lot more easy going. Okay. Okay, so this again, this collab has some more illustrations, but we'll move on. Now, going back to the loss functions, like if I were to consider the loss functions, there's another perspective I get, and the other perspective is that the subgradient descent, it's like it's specific to machine learning. Can we do something even more specific to machine learning? Right? So if I were just dealing with ordinary optimization, my story could end here, right? But I'm dealing with a summation here everywhere, and that makes me think whether I can go stochastic, which is whether I can treat or preferential updates based on certain points will lead to better convergence, or instead of preferential updates, should I just randomly sample points? A lot of work in the recent past has looked at core sets. Core sets are like those points where the updates will be of greater value, right? Better throughput. Support vector machines, for example, support vectors. The support vector points are considered points that help you converge faster, because those are the points that lie on the margin. A subset in general is meant to be very useful in general. Not all points matter equally. Now, we can go to one extreme and say, well, I'm just going to randomly sample a point. You can do it as well. And that's what we'll do for some part of the class. In your seminar and project reading, you'll see a lot more stochasticity. Okay. So I think starting next week or something, your seminar reading has been published, right? So they will publish it. I think your seminar reading will start next week. Seminar presentations. We'll have the half of the class or 3/4 of the class will be presentation, and then I'll continue classes for the rest of the duration. So there you'll see more of these core sets coming, hopefully. But let's get to a little bit more understanding here. For example, what one of our recent approaches called grad match does is says, well, let me look at the gradient of the entire loss and a weighted sum of the gradients of some of the points with respect to some of the points. So why stochastic? So I'm giving one very simple machine learning perspective. If I had the loss evaluated on the ith example, as against that, the loss evaluated on all the examples, I just call it L. Is there a way that a weighted sum of the gradients with respect to the individual points might well approximate the gradient of the entire loss function? That's what we published in our work called grad match. So gradient matching, right? What stochastic says is, well, instead of trying to approximate the entire gradient in an exact sense, let me do it in a probabilistic sense. If I can probabilistically sample a point, and if I find that how well does or assess how well its gradient matches the gradient of the entire loss. So can I characterize how fast I'm converging with respect to a regret if I had access to all the points? So that's one perspective of looking at convergence of stochastic approaches, a regret approach. The other is, well, maybe I can find the points whose weighted sum of gradients might actually approximate the actual gradient. So that's a core set. In core set also you can look at convergence. But more than convergence, now we are going to rest of the this part of the course is just going to be a lot more intuition. We'll hopefully bring up some results to foster the or reinforce the intuitions. For example, crust. There's a NeurIPS 2019 paper. What it does, I given some 3 different ideas, like grad match was one. But what crust does is you cluster the points. Okay, so in each class, you cluster the points. What you're trying to do is that massive gradient, a Jacobian. Jacobian is the matrix of all the gradients. You're trying to separate that into noise and signal. Okay, so if I look at the blue points, which belong to one class, if I wanted the gradient of all these guys, right, this might really not help. It is an outlier. It's just one point by itself. So is there a way I can analytically decompose the Jacobian into a noise component? Think of doing some signal value decomposition and some information component. So that's idea in crust, published in NeurIPS 2019. Not very old, right? There are other ideas as well. So points with high gradient magnitude, with the understanding that gradient norm is uncertainty associated with the example. So if points have very high gradient magnitude, oh, it's very uncertain, pick it up. People have thought about that. Points which are shortest distance from the points of the opposite class. So for example, if this point is very close to another point here, I mean, this might help me discriminate better. That's the idea of support vector machines. So that's in some sense that's what crust does. It does clustering, right? So I know a cluster of points that lie close enough to a separating surface. But I think suffices to say that if you relook at the entire space of stochastic algorithms from the perspective of all these recent advances, right, you see that they are kind of well motivated, but obviously a lot better can be done given deeper insights we have got through both analysis and to some extent computational analysis, mathematical analysis and computational analysis both. Okay, I think there's enough motivation now. And some of it, a lot of it will come in your seminar and projects. So what is the framework? You will have this FW in blue, which is a summation over all the individual data points. And instead of evaluating the full gradient, which requires order n computation, you're going to look at order 1 computation, which is exactly on one point. And you realize that it's a very redundant computation. You don't want to do all the points. So sometimes n is of the order of million or hundreds of millions of data points. So I'll just use this yellow as a new point and gray as old. So I is an index into the example. W is to represent the function parameter. So instead of X, now we'll use W. We are getting more machine learning specific here. Okay. So far we were doing X, X, X everywhere. But let's use machine learning parlance. Of course, then one may wonder, will all the algorithms, including accelerated gradient descent, yes, all of them can hold. Right? You can talk of subgradient, stochastic subgradient. So the basic idea now is going to be just Wt plus 1 is Wt minus. Now I'm going to look at a specific example minus gradient Fi. So now I have an index I into the example. But based on all that wisdom, you can replace the ith gradient with an approximation of the full gradient based on core sets or whatever else you want. Okay, so you want to now start with the simplest of the lot where you sample the points uniformly at random. Again, I keep repeating you. This is simple, but you can think of the more sophisticated crust, grad match, and other schemes. So this is very simple. Iteration becomes n times cheaper than full gradient descent. No brainer, right? So this is a key here. You are only computing this, and therefore you have n times speed up. Right? So then one may ask, okay, if I can get some speed up using a random selection, why not get some better convergence using a random subset of points? That's also possible, right? Instead of doing an intelligent subset of points, this is all intelligent subsetting, intelligent weighing of gradients. I just take a random subset. Maybe it's diverse enough. That also you can do. You can use the submodular functions to determine a diverse set of points and compute their gradients. So that's also possible. Okay. Now the next question. So we are going to go very high level on this. So this is, if this is the update leading to n times speed up, and needless to say, we can have a random subset. You can have informed subset, core set, base subset, and so on. Right? Core means they are also weighted. Question is, how do you analyze these, right? So what will you fill up in the gap there? For convex functions, what were we doing so far? Less than equal to. Can I just do this less than equal to here? Recall that GT was based on a single data point. Can I put a less than equal to blindly there? What can I do? Yes, anyone? Can I do this in expectation? Right. So I know that the summation holds, right? Summation less than equal. Well, I mean, this f is basically summation fi. So this is fine. The right hand side, if there is a summation, I knew there's an inequality. So this holds for complete loss. That's if it were a complete gradient. If I have ith point FIWT minus FIW star, then also it holds. So the extreme case holds. Summation it holds. On each individual data point also it's convex. Let's assume. Even then the problem is when I have a summation on the left hand side and a single data point on the right hand side. Single point contributing to a gradient, stochastic gradient. What do you do? I've just elaborated the same question. I've not answered. Sorry. Shape will change. You'll do a vector. Vector of what? So I think the answer is first of all very simple. It may or may not hold. Okay. So I don't know why you guys are sweating it out. It may or may not hold. It all depends on how that single point has contributed. So itna kyo pasina, right? May or may not hold. Right? But what we exploit is that this holds an expectation. So I can't deal with this directly. I want to talk about this in expectation. Probability means you have to bring expectation. What else, right? So, so what's the expected value of a gradient? It's okay. Empirical average. You can take 1 upon n, right? Now, if you use that if you assume that the GT is an unbiased estimator, that is the expectation coincides with the empirical average, right? There's no bias in the expectation. Then you can kind of show that this inequality holds. Okay, that's when we are interested. We're basically interested for unbiased estimators of the gradient that which makes sense, right? In expectation, you just slap an expectation here, you would expect the inequality to hold. No rocket science here. Is this clear? So what we'll exploit is that, well, there's on the left hand side, there's nothing like expectation, but so it's conditioned on GT WT equals W. Okay, so that's the notion of unbiasedness assumption. in stochastic gradient descent. Right. So the key here is that the point for computing GT was picked uniformly at random. So often it's kind of justified. So the convergence result is that under convexity alone, but under an interesting modification to Lipschitz continuity, which is the Lipschitz continuity in expectation. This is also something you would expect, right? If I have to prove convergence, I'm going to slap an expectation all through. So then I'll start looking at the expectation of the gradient norm, which will mean that I'm looking at Lipschitz continuity in expectation. Okay, so the convergence now is similar. Now, all this starts looking very similar beyond a point for the simplest algorithm. 1 upon square root t, this is also 1 upon square root t. In fact, RB upon square root t is what we started with. Now the B here is different. Where B arises from stochasticity in, from Lipschitz continuity in expectation. Okay. This is an important take home for everyone. Now, how this results, we're going to not get into, but I can assure you it's pretty much the same proof method. I've already given, that's why I spent a lot of time asking you that quiz question. The inequality in expectation sets the ground for the proof, everything in expectation, right? So Lipschitz continued expectation. Otherwise, the choice motivated from subgradient descent we already have for gamma. You know, it minimized one of those steps, the right hand sides. The upper bound was minimized. Okay, for both a gradient and subgradient descent, we have the same result. So left hand side, right hand side, we both have 1 upon square root t. So everything seems to be making sense. Now, if you bring in strong convexity, what happens? Strong convexity with mu. Here, unfortunately, I don't talk about convexity in expectation, strong convexity in expectation. It's just strongly convex function. That's it. So it is almost the same as subgradient descent, but in expectation. So here you'll have b square. Okay. Strong convexity plus Lipschitz continuity in expectation. You'll have almost the same. 1 upon t plus 1. So this is not, by the way, this is not the same as strong convexity earlier. Okay. Now, strong convexity, you have thrown up an advantage that you should realize. Right? A strong convexity, we were never 1 upon t, right? We were at 1 upon t square. We got to as good as log, right? But stochasticity, you may not have those advantages so easily. Of course, you can apply what we discussed at the beginning of today's class. What did we discuss? Where did we begin the class from? Yes? Accelerated. You can apply accelerated here. Let's see if accelerated gives you back some of the lost advantage. Okay. So just to sum up, here you have everything in expectation. Okay. This entire thing in expectation is 1 upon some. Oh, I'm sorry. You have some of the advantage, not completely. There is a 1 upon t into t plus 1. But it's still not as good as what we had for strong convexity. Okay, there's some weighted average here. Mu t is 2 upon mu t plus 1. The right hand side looks similar to strong convexity plus Lipschitz continuity, but there is a bit of a caveat because you're also dealing with this particular weight, 2 upon t into t plus 1 under that scheme. So it may not have that advantage always. Okay, so just to kind of, before we move into any accelerated version, the classical gradient descent, we assume that we had Lipschitz continuity in expectation. We had Lipschitz continuity. So for sum of errors objective, so you look at this 1 upon n summation of the gradient, whole entire square is less than or equal to b square. But now this stochastic gradient descent, it's slightly interesting, right? Here you had a summation, norm of the summation squared. Here you have a summation of norm squares. So, or expected, basically it's an expected squared norms of the stochastic gradients. So you can always apply Jensen's inequality. This is what I was talking about, is the gap, right? I said there is some gap. It's not as rosy as you had for gradient descent. Why? Because if you apply Jensen's inequality, the part in blue is less than or equal to the part in yellow, right? The norm summation squared is less than or equal to summation norm squared. Okay, so that's like the sad part. So on the right hand side is what you get for stochastic gradient descent. That's what we're dealing with right now. Whereas earlier you had this left hand side for gradient descent. So this is a down. Here's the downside. Right? So I don't know whether we'll have time, but there's even in this analysis, there's a silver lining. The silver lining is that if instead of having to do a summation of all the norm squares, if I were to do a norm of summation of norm, in the sense, if I'm able to decompose it into batches, right? One batch norm square summation. So instead of having individual points on the right hand side, if I had groups of points on the right hand side whose norms I took, that's called batch stochastic. That's a motivation for batch, one motivation for batch stochastic. I can do better by grouping points, because then this gap I can try and reduce. Is this clear? So on the right hand side is totally liberal. Every point is isolated. Left hand side, everything is grouped together. Okay, so this is, so what do you think will be? We have only a few minutes left, so I want you to suggest, what could you do to get batch stochastic, right? Bridge this gap. The gap on the slide or gap here. What would you do? How would you form these batches? Yes. We get the intuition, right? So how would you like these batches to be so that the inequality is tightened? We can We can break the summation, that I understand, but still I didn't get an answer to my question. We will break the summation, but you need those batches to be such that, see, you need those batches to help bridge the gap, no? That's the whole point. So what's the worst setting? If every batch consists of similar looking points, what will happen? Every batch is, say, scaled version x, 2x, 3x, 4x. Let's say I just take those to be one batch. What will happen? Will I get any advantage in bridging this inequality? Is the question clear? If I take x plus 2x plus 3x, right? That's what is happening. If I take those groups and then I take a plus y on the left hand side, right? If I take groups, any advantage? No advantage, right? You might as well keep them separate. No difference at all, isn't it correct? Or practically, when will the difference come? When the batch has, so x perpendicular to x, right? You would like these points to be less correlated. Points least correlated with x. Points least correlated. So think about this. The crust, right? I talked about crust where you find clusters of points. They had similar idea, right? You're not looking at all points in one shot. You're looking at groups of points. You pick one point from one cluster, another point from another cluster, instead of all points from the same group. Is this clear? So we'll continue with this batch stochastic gradient, but just as a comparison, before we do that, subgradient descent, we shouldn't even call it descent. Subgradient convex and strongly convex results look very similar. Using stochastic, we can be n times faster, but there's a slight catch. You will be 1 upon square root t for gradient, for convex. For strongly convex, you will be 1 upon t instead of 1 minus mu upon L raised to t. So I've already told you stochastic gives, you take a hit, right? So for smooth problems, stochastic gradient needs a lot more iterations. Yeah, so there are lots of speed up techniques we'll talk about. And this is just a summary, right? For strongly convex, inequality is much bigger, which is a problem. We're not happy. Hopefully, acceleration will help, right? I don't know. We'll see. This is a slightly less gap. And the overall challenge is that the variance of these variance of the norm of gradient seems to be expected to be high. So each iteration is n times faster than the case of full iteration. So that big advantage you have. So you cannot forget that. But there's going to be variance, which you want to reduce. So again, the second perspective. One perspective for batch stochastic is reduces inequality, right? A second perspective is, can it help reduce the variance? They're related perspectives, right? But make a note of these two. So make a note of these two before we move to batch. Perspective one. for batch stochastic. And a perspective 2 is variance reduction. So we are looking to reduce this variance associated with the norm of the gradient. Right? This is a perspective 2. Just remind me to begin the class with these two perspectives next time. Okay. Thanks.